Hello, everyone, and welcome to a video where we look at solving first order differential equations using three techniques. Uh, Namely, first of all, we are going to look at how to solve the easiest first order differential equations, which are easily separable. Followed by, we will talk about homogeneous equations and we'll look at how to solve homogeneous equations using substitution. And finally, we'll look at equations which can be solved using the integrating factor. So let's begin the video. So let's see what a differential equation which is separable looks like. This is perhaps the easiest example of what a separable differential equation looks like. So basically, what it entails is we have to separate the x variable with dx and we have to separate y with dy. So basically we have to bring y and dy on one side and x and dx on one side. So we'll try to separate them this way. So let's take dx on this side, leaving us with dy equals to y over x dx. As you can see, x and dx are on one side of the equation now, but y is still not written with dy. So we'll try and take y on the other side. Remember, I can write this as y into 1 over x dx and this as dy. Now I need to divide y with dy, which will give me dy over y equals to 1 over x dx. As you can see, the x and the dx are now on one side of the equation and y and dy are on the other side. Hence, we've separated the variables on each side of the equation. Moving ahead, I can write dy over y as 1 over y dy, which is equal to 1 over x dx. All that needs to happen now is we need to integrate both sides. As you must know, the integration of 1 over y would be ln of y, which is equals to the integration of 1 over x dx, which should be ln of x, plus a constant which can be written as ln of c. Now remember, when you integrate a function and end up with ln as the integral, as the answer of the integration, you can write the constant as ln of c as well and not only c. So let's try and make y the subject. Using one of the rules of logarithms, we can write this as ln of x times c, and we can have ln of y on this side. All we need to do now is cross out the ln on both sides and y equals to cx. This was one of the very simple examples of how separation of variables work in a differential equation. Let's look at a few more examples of separating variables and how differential equations can be solved by separating variables. So the next example is dy by dx equals x squared plus x squared y squared. Now looking at it uh, initially and trying to separate dx and the x squares on one side and dy and y squared on the other sides seems a bit tricky. But all we have to do is look at how this can be simplified first. So before we get confused about the fact that is it going to be actually separated, is it separable, we need to simplify the equation first. So as you can see, x squared and x squared y squared have something common. So I'll take x squared common and I'll be left with 1 plus y squared. and I'll bring down dy by dx as it is. Now again, we'll try to separate x and dx. We'll try to bring x square and dx on one side and dy and 1 plus y square on the other side. So what I'll do is I'll take dx on this side, which will leave me with dy equals to x squared 1 plus y squared times dx. As you can see, and I'll reiterate, that x square and dx have been brought on one side of the equation, but 1 plus y square is still with these two. So I'll have to take it on this side of the equation. Now I'll write 1 over 1 plus y square dy equals to x squared dx. What needs to happen now is we need to integrate this on both sides, and we will eventually end up with the answer, making y the subject, that is. Let's look at another example of equations where we can separate the variables, the x and the y's on one side. So let's suppose we have dy by dx equals to minus x over y minus 3. This one seems pretty straightforward, and all we have to do is bring dx on this side first, which will leave us with minus x dx, and we can take y minus 3 on that side. So essentially we can cross multiply. This is what we'll end up with, and all we have to do now is integrate both sides. Now integration of y minus 3 would be y squared by 2 minus 3y, and the integration of this would be minus x squared by 2 plus c. In order to make y the subject here, one can always do completing the square and solve. Let's see how that works. So we can have y squared minus 6y over 2 equals minus x squared over 2 plus c. Now what we can do is we can also write this as x squared plus c over 2 and y squared minus 6y over 2. You must be wondering that why didn't I write a 2c over here? Now remember, c is a constant. If you multiply it with a number, it still remains a constant, which is unknown. So you can ignore the 2c. All you have to do is cross out these 2's, and let's now look at what's left of the equation. So we have y squared minus 6y equals to minus x squared plus c. Let's complete the square on this side. So we'll have y squared minus 6y plus, if you divide 6 with 2, you're left with 3. So plus 3 square on both sides. Minus x squared plus 3 square plus c. What we're left with on this side of the equation now is y minus 3 whole square equals to minus x squared plus 9 plus c. Eventually, if we want to make y the subject, we'll have to square root both sides. So squaring both sides will leave us with y minus 3 equals to square root of minus x squared plus 9 plus c. And then eventually y equals minus x squared plus 9 plus c plus 3. Remember, we've not found the value of c because we were not given with any initial boundary conditions in this question. So this is the general solution of our equation and not the unique solution. I hope we are clear about how to solve simple differential equations which involve separation of variables through these examples. I would recommend, if you're not clear about this, then kindly pause the video and look back at one of these examples, perhaps one of these examples again. Now, moving on to the next technique, which I told you about at the start of the video how to use substitution to solve differential equations. Now, as far as this technique of substitution is concerned, one thing needs to be made sure of is that the equation has to be homogeneous. Now, what does a homogeneous differential equation imply? Well, it's simple. If I write a differential equation, let's suppose dy by dx equals to, let's say, x squared plus y squared over 2x squared. Now, as you can see, this differential equation dy by dx is a function of x and y. Now, a homogeneous differential equation is defined as an equation where the function x and y remains the same if you multiply x and y with some constant k. So let's apply this understanding to this equation and see if this is homogeneous or not. So the function we have in place of, so I'll just write f of, I'll just rewrite this here. So this is the condition for an equation to be homogeneous. So the function f of, the function which is of x and y should be equal to f of kx and ky. So I'll just bring the function down. I'll just write the function here, which is x squared plus y squared over 2x squared equals to. Now what I'll do here is, instead of x squared, I will write kx squared plus, instead of y squared, I'll write ky squared. Remember, I'm plugging in place of x, I'm plugging in kx, and in place of y, I'm plugging in ky over, as you can see, it's dividing by 2x squared, so I'll rather write 2 times kx whole squared. Now, if I simplify this side, I end up with k square x squared plus k square y squared over 2k squared x squared. Having said that, k squared can be taken common in the numerator, leaving us with x squared plus y squared over 2k squared x squared. Now, as you can see, k squared cancel out, and we are left with the same answer as the original equation, which means this is homogeneous. This is how you check for homogeneity. All you have to do is write the original equation on one side and write f of kx and ky on the other side and see if you get the same equation back. Now, once we've established an equation is homogeneous, then we can apply substitution to solve a differential equation. So, if I want to solve this equation now, for which I've established this is homogeneous, I will try once to see if separation of variables work. No matter if I take dx square on this side, dx on this side and y on the other side, I'll not be able to separate these variables on either side of the equation. So separation will not work here. And because we've established that this is a homogeneous differential equation, we can use this substitution y over x equals to v. This is normally a substitution used for solving such equations. So all I have to do is make y the subject. So y equals to vx. Remember, this is a normal substitution that we use to solve such type of equations. So from this, I've established that y equals to vx. So I'll replace y with vx wherever I see it. So x squared plus Vx squared. So for y, I wrote Vx over 2x squared. And I have dy by dx on this side. Now, not only this, I need to differentiate this as well to replace dy by dx with something in v. So let's try and differentiate this. So if I differentiate this, I'll be left with dy by dx. And please note, v and x are two separate variables, so I'll have to use the product rule here. The differentiation of x is 1 and v will remain as it is, plus now I'll differentiate v. So the differentiation of v is 1, but I'll write dv by dx here because it's not the original variable that we were differentiating, times x. So dy by dx is actually v plus dv by dx, dv by dx times x. So let's replace dy by dx with this, v plus dv by dx times x, and it's equal to x squared plus v squared x squared over 2x squared. Let's try and simplify this now. So if I look at the numerator on the right side, x squared is common, leaving me with 1 plus v squared over 2x squared, and x squared can cancel. And on this side I have v plus dv over dx times x. Now we can take the v on the other side, leaving us with 1 plus v squared over 2 minus v, and we have dv over dx times x on this side. Let's see what happens now. I'll take the LCM on this side, which will give me 1 plus v squared minus 2v and dv by dx times x. Now I can use the algebraic formula here, as in I can see that it's a perfect square, and I can write this as v minus 1 whole squared over 2, and on this side I have dv by dx times x. Now let's try and separate the x and dx on one side and dv and v on the other side. So what I'll do is I'll cross multiply first up. So I'll have dv times 2x equals to v minus 1 whole squared and times dx. Now let's further separate them. Let's bring 2x on this side and v minus 1 squared on the other side. So we were left with 1 over 2x times dx and dv over v minus 1 whole squared. All we need to do now is rewrite this as 1 over v minus 1 whole squared dv equals 1 over 2x times dx. Now let's integrate these two. So the right side will be written as 1 over 2 times 1 over x dx, and as far as this side is concerned, it can be written as v minus 1 to the power of minus 2 dv and the integral sign. Now let's integrate the right side, which will leave us with 1 over 2 ln of x plus, as I told you at the beginning of the video, if your integration gives you an ln, I repeat, if your integration gives you something in ln, the constant can also be written as ln of c. And integrating this side is pretty straightforward, so it'll become v minus 1 to the power of minus 1 divided by minus 1, just like normal integration works. Now this can be written as minus 1 over v minus 1. So I've just taken the negative power and I've written it in the denominator. On this side we now have 1 over 2 ln of x plus ln of c. Now let's try and apply one of the logarithmic rules here. So I can write this as ln of x raised power 1 over 2 plus ln of c, which can then be simplified as ln of cx raised to the power of 1 by 2. And this side remains minus 1 over v minus 1. Now, since we're almost done with simplifying it, we can bring back the substitution that we used in the first place. So remember, v was equals to y over x. So all I need to do is I need to replace this v with y over x. So minus 1 over y over x minus 1 equals to ln of cx to the power of 1 over 2. Now what we can do is we can take this LCM in the denominator, which will give us x, and y minus x, which is going to be equal to ln of cx power 1 over 2. The x can be brought in the numerator, leaving us with minus x over y minus x equals to ln of cx to the power of 1 over 2. All we have to do is make y the subject, and that will be the general solution of our equation. So we have minus x equals y minus x ln of cx to the power of 1 over 2. Now let's open the brackets, which will give us y ln of, in fact, we can simply take this and divide it with minus x. So we have minus x over ln of c x to the power of 1 over 2, which is equals to y minus x. And the final step in making y the subject would be to add x on the other side. So ln of cx to the power of 1 over 2 plus x, and this is equals to y. This is how integration by substitution works. Remember, in order to use the substitution v equals to y over x, we need to first check whether the equation is homogeneous or not. Now let's talk about the final technique which we discussed at the beginning of the video. Let's see how we can integrate, in fact, how we can solve a differential equation using the integrating factor. In order to use the integrating factor, one thing is of great importance, and that is our differential equation must be in this form. Now, this form basically means you should have dy by dx to begin with plus any function of x, let's suppose 2x, times y equals to any other function of x like 4x squared. So if your equation is written in this form, you can use this technique. Also, if your equation is written in this form, you can still use this technique, although it seems confusing. But please note, if I write the form beneath it, I can then see how this is all the same. So, as you can see, dy by dx is part of both the forms. So both the questions have dy by dx to begin with. Also, as you can see, the the thing written with y over here is minus 3 over x plus 1. So that is our p of x. We also have y in both of these equations, and 2 is q of x. So q of x and p of x don't necessarily have to be functions of x. They could be constant numbers as well. Let's see this once more. If I look at this question, x times dy by dx plus 4y equals to 12. Now, initially when I look at it, it does not follow the form I'm talking about. It does not look like dy by dx plus p of x times y equals to q of x because of the presence of an x here. There's no x in the original form that I'm talking about. But if you look closely, you can divide everything here with x. And once that happens and this x crosses out, then you can see that there is similarity between these two. You have dy by dx to begin with, you have y in both of these equations, and your p of x is 4 over x. So p of x here is 4 over x, and q of x is 12 over x. So as long as your equation follows this form, you can use the integrating factor. And remember, p of x and q of x can be simple numbers as well. So let's look at an example of how to use the integrating factor. So let me write an equation and let's see first of all, is it following the required format? So dy by dx plus 3y, and there's an x here, equals e to the power of x over x squared. Now as you can see, this is not following the general form I just wrote. If I write the general form on top of it, it does not follow it. Reason being that dy by dx is not alone here. There's an x with it. So as I did in the discussion just about a few moments ago, I'll divide everything with x here. So dividing e to the power of x over x will leave me with e over x cube. Please note this down, because e to the power of x over x squared divided by x means you have to eventually multiply it with 1 over x, leaving you with e to the power of x over x cube. Now that we've divided everything with x, we can simplify, and as you can see now, this is following the required format. This equation is in the required format, and p of x is 3 over x, whereas q of x is e to the power of x over x cube. Once you have established that your equation is in this form, all you have to do is find something known as the integrating factor denoted by I. So I is basically the integrating factor. So once you've established your equation is in the required form, you have to find an integrating factor, which is given by e to the power of integration of p of x d of x. So this is the formula to find the integrating factor. Let's apply the formula to this question. Remember, my p of x here is 3 over x. So I'll try and find the integrating factor using this formula. As you can see, I is going to be e to the power of integration of 3 over x dx, which is going to be e to the power of 3 ln x. There's no need to write a constant here, because when finding the integrating factor, we do not write plus c. So no need to write a constant. Now all we need to do is we need to write this as ln of x cube, because the 3 goes there as per one of the logarithm rules. And then e and ln cancel out, which is also a logarithmic rule, giving us an integrating factor of x cube. Now that we found the integrating factor, which is x cube, all that we need to do is multiply all of our equation with x cube. So I'll repeat my steps. In the first step, you have to see if your equation is in this form. And in the second step, you have to find the integrating factor. I'll just get rid of this excess writing. So in step 2, you have to find the integrating factor and multiply it with the entire equation. These are the two steps only. Now that we've found the integrating factor as x cubed, let's multiply it with the entire equation. So we end up with x cubed dy by dx plus 3x squared y equals to e to the power of x. Because when you multiply x cubed with this, 3 over x, then the x and x cubed cancel, giving you x squared. And when you multiply x cubed with this, then x cubed and x cubed cancel, leaving you with e raised power x only. Now, if you look closely on the left side of the equation, all you have is the product rule being applied to this equation, this function. So the product rule, the differentiation of x cube y will give you this. So I have deciphered that this can be written as this. How would I know this for every question? Remember, I have to write y as it is here. So y will always be a part of this, only y. And the second part of this will simply be the integrating factor. I repeat, in order to see which function's differentiation is given and where is the product rule being applied, you always write y as it is and the integrating factor as it is. That's it. So I've replaced x cubed dy by dx plus 3x squared y with this, because the differentiation of this will give me this. So it's just another way of writing it. And this is equal to e to the power of x. Now we can look at separating the variables and we can easily solve. So if I take x cube on the other side, e to the power of x over x cube, I'm left with dy here over dx, and all I have to do is I have to take dx on the other side, e to the power of x over x cube dx and dy. And the final step would be to integrate both sides and make y the subject. Very well. These were the three techniques we apply to solve differential equations. And I hope you liked the video. In our next part, we will further talk about how to see what substitution to use, and we can further look at more examples. Thank you for watching.